Yep, there's taken you to the ellipses. So I'm going to work on ellipses and hyperbolas in one lesson. And bottom line is, all this stuff this week will be due Friday. You can find the time to finish up your work through Friday. All right, over and out. Okay, here we go again. Another day, another dollar. Wrapping these few lessons up so you can be experts at analytical geometry when it comes to conic sections. And what you're looking at are pictures of ellipses. They're a lot like a circle. Let me just remind you the equation that we used in chapter 2 of circles. We always had x squared plus y squared equals to the radius squared. And also we've had x minus a squared plus y minus b. Actually, we didn't use a and b. We used h and k. Why don't I change that to the h, because it had to do with the horizontal movement of the center. And we used a k that stood for the vertical change of the center. Squared equals to r squared. But look what happens on either of these problems. If you divide everything by the r squared in this problem, look what it turns into. It turns into x squared over r squared plus y squared over r squared equals to 1. This one turns into, I can't hardly see my 1. I don't know where there's another square here. This one, oh, I should have said equals to r squared. I thought I had. So if I divide everything by, well, I guess it is in there. Let me just, there, I see it here. There it is. If I divide this side by r squared, divide this side by r squared, then you end up getting x minus h squared over r squared plus y minus k squared over r squared equals to 1. So we've dealt with circles before, but it is a conic section. But what we're going to do is deal with the ellipse. The circle's demented cousin. He's a little deformed. It's not his fault. You call it an oval. You call it an egg. Whatever you want to call it. But geometrically, it's called an ellipse. Now, we're going to talk about some equations and graphs of ellipses. And we're going to start out with the center being at 0, 0, just like we did with circles. And then we are going to, as you see, translate them. That means we're going to move the center, and that takes us to like how I moved the center of the circle. Same thing. Nothing's new under the sun. Okay. Then we're going to talk about a definition of eccentricity. How oval is it, is the question. And I wonder if there's an application of an ellipse, a real world problem. Okay. There is a definition for the ellipse. An ellipse is a set of points. Well, just like a circle. A set of points. A whole bunch of them. In a plane, and the sum of whose distances, so an ellipse has two distances that we're adding up, the sum of two distances from two fixed points is constant. Okay, so no matter how you, well, I guess it's hard to put it in words. I'll have to show it to you. Each fixed point is called a focus. And if you, the plural, and we need plural because two of them are called foci. Now, I'll show you where they are here. Well, there's a picture here. I showed you center. These two are fixed points called foci. And they're fixed. It's like a nail that's in the wood. And what happens is, If you take any point on that ellipse, I'll go here, and we take the distance between this focus to that point and this focus to that point, this is going to be sum number one, no, I shouldn't say sum number one. Let me just change that. I'm going crazy. I'll call this first one, distance one, distance one, distance two, and distance one plus distance two equals to sum. But the ironic thing is, no matter where I move this point, if I move it right here, really looks different. And I again take the distance from this focus, call that distance one, and I'll call this one, or call it 3, or call it 4, whatever. Let me call this one distance 3 and this one distance 4. Well, guess what? Distance 3 plus distance 4 is exactly the same sum. No matter where you draw a point on the ellipse, these distances from the fixed point to the other fixed point will always add up to the same value. That's the beauty of an ellipse, okay? That's the definition of ellipse. As a matter of fact, I got a little secret for you. My father was not a mathematician. He was a welder. He could build things. And here's what they would do if they needed to draw an ellipse. They got their piece of wood, okay, whatever. They put nails in it. They just put nails in it. Then they would tie some string, not too tight, around that string like that. And then what they would do is they'd put their pencil, and then they would pull up on the string. And what they would do is the tension of the string, they would just pull it up, and it can only go so far because of the nails are holding it, right? Then they would just keep doing it even on this side, and they would create a perfect ellipse every single time by moving their pencil on that string, and it's constantly putting tension on it. And my dad, he didn't know. He didn't know that what he did was these nails represented focal points. He didn't know that. So he taught me how to draw one on a piece of wood, and I taught him what that was called mathematically. Is the graph of an ellipse is the graph the function? No, it's not a function because look, it fails the vertical line test. But you could divide that in two graphs, the upper, the plus or minus of something if we were to solve it for y. But we'll get to that. Maybe we'll get to that. Okay, let's see. Does it look familiar to you? It almost looks like a circle, doesn't it? Except there's no R down there. The reason there's no R is because if you were to go to the right, we'd call that A instead of R, which is going to be different than if I go straight up to that and I call that B. If A was equal to B, that would be a circle. But if A does not equal to B, then it's an ellipse. And that's what we have going on right here, okay? Now, this author says, always call A the biggest number. It doesn't really matter, but it does in this formula right here. It helps out right here. If you always call A the biggest number, then this formula, we're going to use this later, but it almost looks like Pythagorean theorem, but it's not. C squared, well, C happens to be where the focal points are. Go ahead, let's look at it. We got a C, we got A's, and we got B's. Well, I already showed you A and B, where they come from. If you have vertices plus or minus A comma 0, what does that mean? Minus A plus A, and they both are at the height of 0. They're endpoints of your, those are your vertices. Endpoints of your minor axis, these are your major axis. Okay, I don't know if he says it. Well, these are vertices. So then if I go the minor axis, 0, 0 go up and minus B, so B, up B, down B. So this axis is smaller than this axis, so we call the longer one your major axis, and this shorter one is your minor axis. Focal points happen on your major axis every single time. And where are they at? Well, the distance C is where that focal point is. You got two of them. I'll call that C2 and I'll call that C1. How do I find that focal point? Is using this formula. If you take your focal point distance and square it, it equals to the difference of A squared, that's larger. If you stick to this connotation, that will always call A the larger number, minus B squared. Okay? The ellipse with the center at the origin will always be x squared over b squared plus y squared over a squared equals to 1. Notice how they switched. But a is still the larger one. But now a squared is underneath y squared. So what does this say? Look at this. Look at the description now. Here's my axes. It has vertices at 0 plus or minus a. Well, now I'm going up a and down a. And the endpoints of the minor axis means smaller axis will be plus or minus b. So then I'm going to go minus b plus b. And look at the shape of this particular ellipse. It's vertical. Whereas this one was horizontal. So if we always call a the larger number, if your larger number squared is under the x's, it's a horizontal ellipse. If your larger number squared is under the y's, then we know it's a vertical ellipse. See the pictures? Horizontal and vertical. Okay. And the formula c squared equals a squared minus b squared. C squared now equals b squared minus a squared. Why? Because our a was on the minor axis. Okay, but look at it. It's still the same idea. That's still a distance of c. But because now a is the endpoint of the minor or the larger axis, which it always was, but now it's vertical, c now is b squared minus a squared. So you might want to write down the formulas. When using the relationship c squared is a squared minus, choose a squared and b squared so that, well, I'm just going to say this. You want c squared has to be greater than 0. Because why? If c squared was not greater than 0 and you tried doing the square root of both sides of a negative number, like a -4, you can't take the square root of a negative number. So you want to rearrange your a squared and b squared to make sure you always get that c squared is always going to be your big number minus your small number. Your big number minus your small number. Okay. Let's try it. We're going to graph ellipses, center there. Now what I do is I always want to get a 1 over here. So I'm going to divide by this, like I did on that first page where I divided by r squared. Well, this time I'm dividing by whatever that number is. It's not called r now. So what happens is 36 over 36 is 1. But now, here's my trick. You got a fraction here. You got 4 out of 36. Don't think of it as 4 out of 36. Think of it as 36 divided by 4. Because that's really what's happening. 36 divided by 4, that 4 cancels out, leaving a 9 down here. 36 out of 4 is a 9. And then 36 divided by 9 is a 4. So take that bottom number, divide it by that top number. So what it turns into, x squared over 9 plus y squared over 4 equals to 1. Now, I can tell that this is going to be a horizontal ellipse. Why? Because the 9 is bigger than the 4, and it's underneath the x. Now, you got to be careful. I don't want 9 and 4. I want the square root of 9. So I want you to think of this as x squared over 3 squared plus y squared over 2 squared equals to 1. That way you know that A is 3 and B is 2. He's also going to want me to find the coordinates of the foci. Okay, and then he goes back to the domain and range. We'll do that one or two times. But so I need to know what C is. Remember, C squared is always, well, in this case for sure, A squared minus B squared, because the A is under the X, so it's always the bigger minus the smallest. So 9, I already had it up here, 9 minus 4. C squared is 9 minus 4. C squared is 5. C is equal to square root of 5, plus or minus. So that's what C is. C is plus or minus square root of 5, and that means from the center of the circle. So is the 3 from the center of the circle. So is the 2 from the center of the circle. Center, 3. Center, -3. From the center, 3. Now, from the center up and down is 2 and a -2. Now, you know, and I know, I'm just not a good artist. But, you know, try your best to try to make it a smooth curve. Well, that just backfired on me. Try that one again here. A smooth curve. Continue the egg, and, you know, it's not going to be perfect because it's so small. If it was bigger, we could do a better job. Now, the question is, where in the world would be the center? Remember, center was 0, 0. So I need 0 plus the square root of 5 and 0 minus the square root of 5 from the center. And how big is square root of 5? It's a little bigger than 2. So I'll go here, and I'll go here. Okay, a little bigger than 2. So there is my focus 1 and focus 2. So don't be afraid to actually list the focal points. He does say he wants the coordinates. So where are they at? That one is at square root of 5 comma 0. Call that focal, what did I call it? Focal 2. And focal 1 is at 0, negative square root of 5. Let's do the domain and range. It's very simple. Just talk about these 4 points. Domain, all the x numbers, -3 to 3. Every x value between -3 and 3. Let me use bracket because it does include them. Range, the minor axis this time, up 2, down 2. So between -2 and 2. So it's a lot of work. B. All right, now he's tricking you. He's got stuff scrambled all over the place. I need to get the y squared with the x squared. So I hope you see right off the bat, 4x squared plus y squared equals 64. Okay, that helps. Divide both sides by 64. That means everything by 64. Everything by 64. And remember what I said. You take the 64 divided by the numerator. So that gives me, how many 4s going to 64? So that gives me an x squared. I know it's a 16, because 16 times 4 is 64. Y squared still over 64, because 64 divided by the 1 is still 64, equals to 1. Go ahead, take a second out of your life and write it as x squared over 4 squared, so that you know that a or b is a 4, and plus y squared over 8 squared. 8, this one changed. This one changed. I'm still going to say a is 8. I'm still going to say b is a 2. But c squared will still be the bigger number. A squared, well, the way he did it, he called it, did he switch them? I'm trying to remember his notes. I'm not sure if he did it right. Because he did the b squared minus a squared. That would only be true if you didn't keep the big one. I think he messed up in those notes over there. Because if I say, I'm still going to say a squared minus b squared, because I need the bigger one. I need the 64 minus the 16. I can't switch it. So I think if you go back to those notes on this thing, following along with what the author wrote, I'll look at it too. Maybe it was me. Maybe I didn't see it right. But it should always be the bigger number, because you're going to have to take the square root in a minute. C squared is 64 minus 16. Is it 48? Or 58? No, it's 48, right? 48 plus 16, 58. 58, yeah, 48. So I got to take the square root of both sides. And that's going to give me c is plus or minus the square root of 48, which you know is plus or minus the square root of 4 times the square root of 12, which is plus or minus 2 square roots of 4 square roots of 3. Does that bring back memories from college algebra? Which is plus or minus 2 times 2 is 4 square roots of 3. That is C, okay? Good news, we're still at the center 0, 0. We still know the center is still 0, 0 because nothing was being added or subtracted from the x and the y. So I'm going to go back here. 0, 0 is my center. I need to go on the x-axis. I need to go the 4 to the right, 4 to the left, and then I need to go on the y-axis 8 up and 8 down. 8 up, 8 down. And I can see right now, please don't draw a star. Please don't draw a star. I am not an expert, and I'm not going to pretend I'm even close to how good some of you can draw, but at least pretend to make it as best of an egg as you can, and that's just a freehand. I'm not trying to be perfect right now. If I really wanted it perfect, I would probably use a computer program and say, put me an ellipse right there, okay? Now, what haven't I done? I haven't labeled the focal points, but I know where they are. From the center, you have to always take the center, which was 0. In this case, I need this 0, the y value of the center. Why do I know it's the y value? Because my focal points have to be on the major axis. It has to be up in here. So you take the y value plus or minus. So it's always going to be 0 plus or minus. And I'm just doing that because I want you to realize that sometimes the center is not at 0, 0, plus or minus 4 square roots of 3. So I go up. How big is 4 square roots of 3? Well, square root of 3 is approximately 1 point... what is it? Well, obviously it's bigger than 4 and less than 5. So let me just go up 1, 2, 3, 4, 5. I don't think it can be bigger than 5, because that would have been the square root of 25. And no, that is 5. Yeah, square root of 25 is 5. And I had 48. Maybe I'm wrong. Let me pause and use my calculator for a minute. Maybe it's 1.7 times 4. I'm going to write that out. Just say, is it 4 times 1.7? approximately. Let's see. I'll be right back. Yep. It was 1.7 something, even close to 1.8 if you want to. So, yeah, it's bigger than what I said because 4 times 1 is 4. 4 times 7 is 28. So it's 4 plus almost a 3. So that's 28, 4, 6, 6.8. So did I have room to go 6.8? I certainly did. Okay, I knew that looked too small when I drew it. So let me get rid of that. Hide the evidence of being silly. About, what did I say, 6.8? So that's roughly about up here. And then down here. Okay. Focal 1. Focus 2. And you know, that would be 0, comma, 4 square roots of 3. This one is 0, comma, negative 4 square roots of 3 are my coordinates. You technically should put your coordinates for everything, and I kind of did. I didn't name this 4, 0. I could have. I could have named this as 0, 8. The more you do, the better you'll start understanding it. All right. Okay. Number 2. Right? We're flipping it around. We're going to do writing the equation. And let me draw what I see here. Write an equation ellipse having the center of the origin. Okay, so here's my graph. Here is my origin. He said I have a foci at 0, 3 and 0, negative 3. 0, 3, 1, 2, 3. I have a focus up there. 1, 2, 3. I have a focus down here. Call that focus 1, focus 2. 0. This is 0, negative 3. This is 0, 3. And so, he says the maximum length, the major axis length is 8. Well, those focal points have to be on the major axis. So I went up to 3 for the focus. I got to go up one more to get a vertex of the major axis at 4 and negative 4. Did he tell me where the other vertices go of the minor? No, he doesn't. So let me just pretend to draw what it could look like. It's a vertical ellipse. So I know part of my equation. Let's see, it's centered at the 0, 0, so I know I got x squared over, well, it's not horizontal, so I don't know what b squared is. But I do know what a squared is. A squared has to be the distance from the center to the endpoint. That's a 4. 4 squared equals to 1. Now, where am I going to get that b? How am I going to figure out what this value is? I'm going to use my magic formula that said c squared is always going to be equal to a squared minus b squared. A's always got to be the bigger one. And I got that when it was 4. So c squared must be equal to 4 squared minus b squared. But what's c squared? C was the distance from the center to the focal point. That's a 3. So that's 3 squared, or 9, equals to 16 minus b squared. 9 minus 16 equals negative b squared. 9 minus 16, that's a negative 7 equals to negative b squared. Get rid of the negative 7 equals to b squared, which is what I want. I want b squared. See, if I keep going and I do the square root both sides, there's nothing wrong with that, but you got to be careful. b is the square root of 7. But b doesn't go here unless you write, if I write x squared over the square root of 7 squared plus y squared over 4 squared is 1. That's fine. But remember, that turns into x squared over 7 plus y squared over 16 equals to 1. So there is your equation that I'm sticking with. And what does a, b, and c represent in the standard form of the equation of the ellipse? Well, we know a and b is really a is half the length of the major axis. Because I go up 8, I go up 4. The whole thing was 8, so I go up 4. That's my a up here. That was half. B is half the length. I don't know if our book even calls those vertices. But anyway, I do. There are 4 vertices. C is the distance from the center to a focal point. I think this is important to conceptualize. Okay? Let's move on. I should get marked wrong for this. Wait, not this one. Where was the half a circle? Graphing a half ellipse. Well, the reason we graph half an ellipse is because with our calculator, we can do a half of an ellipse. I mean, I'm going to pick a different problem first. Let me pick a different problem just to show you. If I gave you x squared over 4 plus y squared over 2 equals to 1, and you want to graph that ellipse with our calculator, you got to solve it for y. So what I would do first of all is get rid of the denominator. So I'll multiply everything by a 4. Because look what happens. 4 goes into 4 once, leaving the x squared. 2 goes into 4 twice, so that cancels out, leaving a plus 2y squared equals to 4. Now get rid of the x squared. 2y squared equals to 4 minus x squared. Now get rid of the 2. Y squared equals 2 minus 1/2 x squared. Now get rid of the squared by doing the square root both sides. Y is plus or minus the square root of 2 minus 1/2 x squared. Da-da! Now you can use your graphing calculator and graph that ellipse. You graph y1 as the positive 2 plus a half, or 2 minus, I'm sorry. I made up the problem, so I can make up the answer. Minus 1/2 x squared. And y2 would be negative of square root of 2 minus 1/2 x squared. Okay? Try it out. Graph that two of those, and see if you don't get a beautiful ellipse. All right, what did he want us to do? He has the equation halfway solved, I guess. But he wants me to graph it. Well, if I'm using my calculator, all I would do with my calculator, I would multiply both sides by 4. Y equals 4 square root of 1 minus x squared over 25. Okay? Make sure you got that over 25 is inside the radical. So you can get your calculator answer. And it's not plus or minus because it's already square rooted. So you're only going to get half of the ellipse. But this is sort of confusing. So if I'm going to do it by hand, I will square both sides. I will square this side, and I will square this side to get rid of that square root. So what am I looking at? I'm really looking at y squared over 16 equals to 1 minus x squared over 25. Oh, do you see where I'm going with it? Move the x squared over 25 over. X squared over 25 to the left plus the y squared over 16 equals to 1. Okay, this is easy to graph. It's centered at 0, 0. A is equal to 5. B is equal to 4. C, if I needed it, would be 25 minus 16. C squared is 25 minus 16. That's my A squared minus B squared. C squared is 9. C is 3. So I can graph everything. And then he wants, again, the domain and range, which is really kind of silly. It's like a circle. You're not really going to go crazy. So let me graph it. I did all this work by hand, so I'm not using a calculator. I need to go 5 to the left of the center 0, 0. So here. 5 to the right. That's fine. What was my B? My B is a 4, because 4 squared is 16. Right? Right here. I'm getting it right here. So I'm going to go up 4, down 4. Now go ahead. It's not going to look very elliptical because 4 and 5 are very close together. So good luck. Good luck at not making a circle. It's so close to a circle, it's crazy. Okay. And then over here at 3, my major axis is 3 and negative 3 is my focal points. Domain is all the x's between negative 5 and 5, including them. And the range is all the y values from the negative 4 to 4. And I think I did everything he wanted, okay? I even did extra. I even showed you how to graph it with your calculator real fast. All right, time to move the ellipse. Guys, I don't want to beat a horse in the head here. We know that minus h means I'm moving to the right h. I'm moving down, but it's actually becomes plus and down. It's down. Remember, it's always going to be the opposite of what you see. If you see a plus, then we're moving left. If you see a plus, okay, then you're moving down. If you see a minus k, you're going up k. So looking at this equation and also looking at that picture over here, if he obviously went to the right and went up. Why did he go right? Because he's assuming that, did he say anything about what h is? Well, no, he didn't. He didn't tell you anything. But anyway, so my major axes, I don't know what he wants. He wants the length. He wants the length. I don't know. Major axis would be, he already said that A was bigger than B, right over here. So that's my major. So it's going to be, how am I going to put it? If you're moving your center over, it's probably easier to do that, to find those vertices first. I know the center will be at h, comma, k. Right here, h, comma, k. See it? H, comma, k. It'll always be h, comma, k. But h could be negative, remember? If this was a plus, x plus h, that meant x minus h. So therefore, you're going to the left. If you see a plus, I'm moving left. So major axis, and still not sure what he wanted me to write there. I'll just think about it for a minute. Guys, I got to back up one thing because I see I had a whole ellipse there, and the last problem with, up here, guys, I messed up. I don't have the bottom part of the answer. Let me erase it. It's not plus or minus. Hello, Cartwright. It was just a semi-ellipse. All right, I feel better. Back to this. Okay. what was I talking about down here? Oh, we were looking at this ellipse here. That was obviously shifted to the right and it shifted up. And let's talk about it being, well, there's two kinds here. Let me erase this. Let me start that part over. I mean, you got nothing else to do, right? I actually want to do all the, come on. All right, I like that picture over there. There's two pictures here, if you look. There is a squared underneath the x. That would be my, like this one, horizontal. Then he's doing one where the a squared is down here, so that's my vertical ellipse. I think what he wants to know is where are the vertices, where are the foci? Okay, so we got to look at our picture for a minute. We'll try to analyze it. So I already gave you the answer here. The major axis in this case is horizontal. Okay. I thought he wanted the length of it, but the length, I'll tell you what the length will always be. It'll always be 2 times A. Because if whatever A distance is, you take double that, you go A to the right and A to the left, no matter where your center is, you're going to get 2A is the length. So I'll write that out. That's good to know. Vertices on the major axis. Okay, look at this here. If it's a horizontal ellipse, you have to move H over. There's the center, H, to get to the center. Once you're at H, that's the X number, excuse me, you will add A to it. This X is H plus A. This number here, the other vertex, is the H minus A, because you're going to go A this way. H minus A. How high am I going? I'm going up to the height of K for both of those. So I think I'm going to write one vertex is at H plus A, and I go up K. The other vertex will be H plus, no, H, I just got done saying it. H minus A, go up K. The focal point looks just like the vertex. I go to H, and now I have to go to the right to the letter C. Not to the A, to the C. Because that's the distance from the center. And I go up K. So here goes. I'm going to go H plus C, comma K. H minus C, comma K. Should give me, if we're going, H is very important because H is where I'm starting out my center. H and H plus C plus A. Look at the vertical. This time, my vertex is up here and here. My focal points are here and here. You notice that the H value never changes. But now the K changes because the K is how high I go for the center. I go up K. But now I got to take K and add A to get that one. Take K, subtract A to get that one. Take K and add the C value to get to that one. Take away C to get to that focal. Let's say I can repeat myself. My major axis is vertical. And the length, I'm still going to say the same thing because what we're doing, we're making A always be on the long side, is 2A. The length of the minor axis obviously will be 2b if they call it an axis. Some books don't call it an axis. I call it an axis. The vertices. This time, I'm going to stay at h, but I'm going to take the k and add a. And the other one will be stay at h, take k minus a. Focus, stay at h, k plus c distance, stay at h, k minus c distance. Ugh, that was complicated. When graphing ellipses, remember that the location of a squared or the greater denominator, I like that better, determines whether the ellipse has a or a blank. Or a blank major axis. Oh, vertical and horizontal. Okay. Yeah. Depends on where you look at it. Vertical or a horizontal major axis. All right, moving on here. Okay, it's already in standard form. I don't have to divide anything. It's already perfect for me. Find the center. Center, opposite of what you see, 2. Opposite of what you see, -1. Find it. A, we'll take the bigger number. What is the square root of 16? It is 4. B, and why did I choose that one to be the A? Because it's bigger. B is the square root of 9, which is 3. So I'm going to go find my 2, -1, right here. That's my H, K, okay? This is my H. Let's see if it works, the formula that I gave. This is my K. So to get to my vertices, first of all, this is, this is vertical. So that means my major axis falls on this dotted line. It doesn't, it's vertical. So wherever I put H, that's stuck there, okay? So that's my center. So if my H stays constant. So now I got to go H plus A, H minus A. Not H, I'm sorry, I was vertical. K. K plus A, K minus A. So I start at -1. And from counting from -1, I got to count 4. 1, 2, 3, 4. Down from there. 1, 2, 3, 4. This distance is 4. This distance is 4. The total length is 8. B, I go to the center again. Right here. That's my center. And I have to go left and right 3. 1, 2, 3. 1, 2, 3. And you probably should label like your major axis. What were those ordered pairs? Well, it was 2, and then I took a -1. I had 4. So count them again. Where are you at? 1, 2, 3. I'm at 3. I'm at -1. 1, 2. So you -1. Then how far? I need 1, 2. That's a -5. It even says that -5. 2, -5. Okay. That was my major. And my minor endpoints would be the minor ones. I keep the K, which was a -1, and then I went 3 to the left and 3 to the right. So it's -1 plus 3. That would be -1 plus 3 was a 2. Well, was it? -1 plus 3? No, it wasn't -1 because I'm going left and right. 2 plus 4. It went to a 6. Why doesn't it like 6? Did I not count right? 2 plus 3 is 5. There it is. That's better. Sorry. That distance is your B. Yeah, 5. 5, -1. And the other one was, looks to me like a -1, -1. Does he want focal points and all that? Typically, you do put everything, but I know time is money. Let's see. Let me draw it. Not too bad. Not too good either. Okay. Focal points. Focal point 1. I need C. I don't he has C. So C squared must be equal to that big number, 16. So that's my A squared. Minus my B squared was 9, wasn't it? 3 times, yes. Big number minus a small number. C squared is, we had this before, 7. C is square root of 7, which is less than 3 but bigger than 2. That means I got to count less than 3, bigger than 2. 1, 2. I can't go all the way to the 3, so I go here. I should make that a different color. And that's focal 1. Then I go to the center. 1, 2, can't go to 3, less than 3. I'll call that focal 2. Feel free to name those. The x value was same as the other x values. It's still a 2, because that's where the center, I should have called that center anyway, instead of the letter C. So it's 2 focal points. F1 was 2, comma, oh, I have it down there. It was 2, comma, be careful. What was the K? The K was a -1. -1 plus square root of 7, and F2 was 2, comma, -1 minus square root of 7. It gets complicated when you start labeling them. If A equals to B, then the equation of the ellipse turns into what? A circle. Okay, eccentricity. How oval is it? Okay. Let's see if we can see what is my going on here. Why is my got dots going? Oh, I hit this weird button. All right. A conic is a set of all points P of x in a plane such that the ratio of the distance from P to a fixed point and the distance from P to a fixed line is constant. Okay, interesting. Okay, every parabola has eccentricity. Well, we know if we had a parabola in terms of the conic section. We already know that the fixed point is called focus point. That's inside. It has that focus point up here. And it has a fixed line the same distance apart. We call that the directrix, remember? Focus and directrix. And so, by definition, these two distances are always the same. As a point moves on this parabola, I told you that the distance from this fixed point to the parabola is the same distance to the fixed point. Those are the same distance. So we say the eccentricity of a parabola is always 1. Now, ellipses is different because we're talking about an ellipse, and if I talk about the focal point, here's your center right here, here's your focal point. We know this distance here is the C distance, right? Well, C has to be greater than 0, but it has to be less than 1. Well, not okay. It's not 1 yet. It's less than A. Why is it less than A? Because as you A is here. A is out here. That's A. You can't go all the way to A because then you wouldn't have a focus point. That'd be not an ellipse. The focus has to be within that interval. So what we do here, I knew I wanted a 1 here. If I divide everything by A, divide by A, divide by A, divide by A, well, miraculously, that means still 0 is less than C over A, which is less than 1. So this is my eccentricity. This is my eccentricity. Less than 1, greater than 0. So in English, eccentricity is C over A. Okay? And it's between 0 and 1. Of an ellipse, this is just an ellipse. Parabola, we already know eccentricity is always exactly 1. Every ellipse has eccentricity of C over A. I hope that's what he wants. Remember, the eccentricity of the ellipse is, it's more elliptical the closer you get to the, it gets skinnier. You get a skinnier ellipse as you get closer to 1. Unfortunately, a circle, your focal point and the vertex are at the A is the same place. So your focal point is on the edge of the circle. So it's not elliptical at all. So your eccentricity for a circle will be 0 because it doesn't have an egg shape at all. Okay, so 0. All right, find the eccentricity for these ellipses. Well, I gave you the formula already. Eccentricity is C over A. So unfortunately, do I have C? I don't have it yet. C squared is the bigger number A squared minus the B squared. So in this case, 16 minus 9 is my C squared. 16 minus 9, we had this come up again like it's a 7, right? So C is the plus or minus the square root of 7. So I'm going to take square root of 7 divided by A. Now, A is the square root of that big number, 4. Eccentricity, it's approximately, let me go to my calculator. .66. Anybody want to agree with me or disagree? Let me go look. Yeah, approximately 0.66 rounded. Okay. So it's a far cry from a 0. It's going to be closer. It's going to be more elongated than a circle, that's for sure. All right, this one, he's tricking me. So I can't find C or A. So E is C over A, but I don't know what this is. I got to do some work. Divide by 50, divide by 50, divide by 50. X squared over 10. Y squared over 5 equals 1. So A squared is 10. A is the square root of 10. And that's what I need. I need it. Oh, I need my B squared too. My B squared is 5. B is the square root of 5. I don't need B. But I do need A squared and B squared to find C squared. C squared is the 10 minus the 5, which C squared is 5. So C is the square root of 5, plus or minus if you need them both. So that will give me square root of 5 over the A, and the A was, be careful, the A is not 10. The A is square root of 10. Square root of 5 over the square root of 10 is the same thing as square root of a half, which is a square root of 0.5. So let's go use my calculator. I'll be right back. Did you miss me? I'm back. That's approximately 0.7071. So it has even a higher eccentricity than the other. Okay. Okay, application, let's see, applying the equivalence to the orbit of a planet. Well, that makes a perfectly good application because planets go around the sun, elliptical orbits. The orbit of the planet Mars is an ellipse with the sun as the focus. Interesting. The eccentricity of the ellipse is, he gave me the answer already for C over A. And the closest distance that Mars comes to the sun is 128.5 million miles. Find the maximum distance of Mars from the sun. So we got Mars, and it goes around the sun. Here's the sun. So as it goes around, well, everything goes around the sun, but he's like, just like Mars, the ellipse, the sun was one of the focus points. So the center of its orbit must be over here. Let me change the color. Here's the center of this path that Mars is traveling. So this sun is a focal point. So we want to know basically the maximum distance from Mars to the sun. We're basically trying to calculate that distance here. We'll call it A. So let's see. Eccentricity is C over A. He gave me the eccentricity, 0.0935. So 0.0935 equals to the eccentricity, and C is the distance from the sun from the center of the orbit. Does he give me any extra answer? He says Mars comes close to the sun. The closest distance that Mars comes to the sun is 128.5 million miles. Wait a minute. Closest distance. Oh, the sun's right here. I'm sorry. That would be 128.5 million miles. That's that distance. So this distance here, this total distance from the center is A, and then this is my C. So if you think about it, A minus C, all of A minus C is this 128.5 million miles. I need to have C, so let me solve this for C. A minus 128.5 million miles is C. And so there it is. I'm going to put, here's my, if this is all equal to C over A, must be 0.0915, the eccentricity. I can solve that for A. Multiply both sides by A times 0.0915 equals A minus 128.5 million miles. Let's get all the A's on one side. Well, actually, let me just do this. Minus 1A, minus 1A. So this is going to be 0.0915A minus 1A, which is going to be a minus 1a. Is that going to be right? That's minus 1a. Oh, yeah, equals to the negative. That's the a minus. Negative 128.5 million miles. All right. So, yeah, that's going to be hard to do the math. I don't want to do it. 1.000.9.0915. Wouldn't it be easier to go to the calculator? Carry a 1. I'll probably get it wrong. Carry the 1. That's a 5. Carry a 1. That gives me 10 minus 2 is 8. 10 minus 10. Oh, wait, that's going to give me that was a 0. And then 0 minus 1. That's 10 minus 0.9. 0.985? 0.85? Let me use my calculator. Let's double check. I think I wrote the number wrong. 0.0935. Oh, this whole time. I can't read my handwriting. It is a 3.5. Ay. Where is that at? 0.9. I put a 1 here. 3.5. 0.935. All right, I'm just going to use my calculator and finish solving it for A. A is, be right back. 141.8 million miles. I guess that was my unit. Is approximate. Wow, that's a lot. I'll run with it. Last one. What is that? A lithotripter? I don't know. This is a machine used to crush kidneys. Oh, you guys should know this, you medical people. Crush kidney stones with shock waves. The patient is placed on an elliptical tub with the kidney stone as one focus of the ellipse. Wow. You can walk away saying my kidney was a focus. A beam is projected from the other focus to the tub so that it reflects to hit the kidney stone. If a lithotripter, whatever is based on the there's the elliptical equation, determine how many units both the kidney stone and source of the beam must be placed from the center of the ellipse. How many units both the kidney stone and the source of the beam must be placed from the center? Oh, how many units both the kidney and be placed from the center? Okay, because they're both ellipses. Okay, so we're just looking for the ellipses. The focal points. So C squared equal to A squared minus B squared, and we're going to use, this is my A squared, this is my B squared. So C squared is 36 minus 27. This is an interesting problem. C is the square root of 9. Yeah, right? 36 minus 27 is 9. So C is plus or minus 3. So from the center of the ellipse is going to be 3 units from each side. The only thing you could do better is to just say, 0, 3, and 0, negative 3. And there is the next lesson, hyperbolas. I think I'll save this document first and upload it, then I'll come back and do this one.